Okay, so I'm having 7.3. 7.3, we're talking about the central limit theorems for sample proportion. Sample proportion, we're talking about p hat, like we did talk about in 7.2. So now we are having, we call this theorem, whatever that you have learned from 7.1, 7.2, is will support the section. Identify conditions needed to apply the central limit theorem for proportions. And we're using the central limit theorem for proportion to describe sampling distribution of the sample proportion and to find probability. So it's kind of a bit more complicated when you're reading this, right? However, we take step by step to figure it out how to do it. And here is 7.3. It looked like we're having a lot of information related to the main idea. The central limit theorem is for this one only, because central limit theorem apply for many distribution. But here we're talking about central limit theorem apply for the sample proportion. Okay, so we use to estimate proportion in a population. And we tells us that if some basic conditions are met, the sampling distribution of the sample proportion is close to normal distribution. You have learned normal distribution in chapter 6. Right? Normal distribution is symmetric and look like a bell shape. It's helping us to compute probability quicker, right? You did compute probability from the left tail, the right tail, the middle tail by using StatCrunch. They're similar, okay? So it's helping us to compute standard error first, then you will kind of find the probability easier. Probability under the graph easier. And here go back to the formula below is kind of similar to the last section, the last part of 7.2, right? If we take a random sample of a population, and if the sample size is large, and the population size is much larger, so then the sampling distribution of p hat is approximately normal with a mean of p and a standard deviation of the following. So if you know the value of p, you can substitute the value for p hat. Actually, let me see, would like to, okay, make sure that it's not draw on here. We having if you don't know the value of p, we can use p hat replace to p. Okay, that's what it means. It means if they don't provide us p, we can write SES square root of p hat times 1 minus p hat divided by n. We can use this if they provide us p hat. Okay. Okay, let me go back this. All right. So again, if you have questions, please email me right away. When you're watching the video and you don't get it or something, or you keep going and then still don't get it, you can email me. So here will be the components that the conditions before you can find SE, you can find the standard error. Usually you have to go to this 3 process before you will finding the standard error for p hat. So first, in a story, you have to make sure that story is sampling. Okay, sampling is random and independent. It means they have to be independent. They not affect of each other of every sampling. Okay, and again, this all the time happen. Number 1, all the time happen. Number 2, large sample. In order to check if they all have enough, the sample size is enough, large enough, you're using formula. You're using this formula for me. You have to try 2. Okay, you have to take n, which is sample size, times p hat, You plug in the value that they provide in the story, compute that, and see what value that you have. Compare with 10. Is it larger than 10 or equal to 10? If it's larger than 10 or equal to 10, that's qualified. And similar to n times 1 minus p hat here, same thing. It has to be greater than 10 or equal to 10 in order to satisfy second condition. Number 3, you have to make sure you take the populations. You have to make sure that the population have to be, you take 10, multiply with the sample size. Okay? Just check that, you know, just the value, like after you compute, you just give me the value. For example, the sample size is 100. You take that 100 multiplied by 10, give you 1000. That's big enough. Just give me a value like this, then you'll be fine. Must be at least 10 times larger than the sample size. That's why you multiply by 10 to make it larger than 10. So that is the way that they are testing. They are estimating the population will be like, okay, larger than 10. Okay. The other time assume had to be 10 times larger. So this figure shows the sampling distribution of p hat for 10,000 samplings, a sample of size 10. So this we're talking about size 10 for each, right? Each is a sample. And the total is 10,000. That's what you having right here. Frequency is 10, 1,000, 2,000, 3,000 right there. Oh. Note that this does not satisfy condition 2 of the central limit theorem. The sample size is too small and the distribution is not normal. You look at the distribution is not normal because it looks like it's skewed to the right, right? Right, it looks like skew right more. You can write just one of the fact that you see, then you might say it's not satisfied. Since it's not satisfied central limit theorem, you should not apply. That means it's telling you it's not enough information for you to keep computing standard error in order to find the true populations. Then you can stop. Okay, you say that it's not satisfied condition 2, I cannot apply anything. But look back the simulation 3. You look at this picture graph right here is symmetric, right? Because they draw the size is 100 at the time, and they draw 10,000 times. So it's too much. It's enough for them to form a normal shape, normal distributions. So that's why after they satisfy with all of the 3 conditions of the central limit theorem, then you are welcome to using to find the standard error. That's your next step. After that, you've done that, you find the standard error by using the value that they have. Okay, and we found the error will be 0.0433. It means like about 4.3% that you might get wrong to estimating the populations, just like about 4.3% only. It's very small. But if we are having like the size is drawn like 10,000, I believe the standard error here is even smaller. Okay, so that's what it means about the standard deviations. Okay, so after you checking 3 conditions satisfied, you can find a standard error. So next, so here is the example for us to do. So this example is important. I think you should mark somewhere. I'll write it down. This is the application for what we have learned from chapter section 1.1, 1.2, and here is 7.3. We are according to 59% of the veterans are women. They given us, what is it here? Statistics, right? Suppose a random sample of 500 veterans is taken. So this is like the sample size, n. What is the approximate probability? So now we have to find the probability of what? That the proportion of the females in our sample will be more, this is the keywords, will be more than 63%. Okay, so will be more than 63%. This is the value that it's like we have to compute the probability. We have to find the probability that x would, I will assume x as the unknown, x will be greater, be more than, right? You might write greater or equal to 63%. 63%. Or you can write P of x greater or equal to 0.63. Then we have to compute this probability. Okay, so this and that will be the same thing, but you have to write this on your test, or you might you know, like copy and paste from StatQuant exactly. Let me see this before you turn in your work. So how do we compute this? Again, in order to do this, I recommend you to testing if the central limit theorem apply. So this, of course, is random sampling. So right here is like this random sample is independent, right? Random and independent. That's the first condition. The second condition, you have to find n times p or p hat. Is it testing is greater than 10 or not? And also you're testing for n times 1 minus p or p hat. Check this if it's greater than 10 or not. Do this for second condition and apply the math in. We have 500 right there for n. 59% is mean 0.59. Plug it here, multiply them together. Let me know if it's greater than 10. Doing the same thing for the second here. So you have to do this and this to testing for the second condition. The third condition, you will take 500 multiplied by 10, give us like about the population we are estimating about 5,000. And from there, you can go ahead and starting finding standard error by using the formula of the standard error, and then you can go ahead and find P. So they have too many steps. So now I would like to go step by step to solve for this one. Okay. So let me erase this first, then we move to the next page. You can see the detail. Okay, first check the conditions. Okay, the sample was random and independent. Second, large sample size. You take that, multiply by 0.59. We have this, of course, it's greater than 10. And you check with n times 1 minus p, you got 205 is greater than 10. That's the second condition. The third condition is, again, you're testing for these three conditions when you are having the problem related to, we call sampling, random sampling, distribution problem. Then you would apply this three. Otherwise, you don't have to. 3, we can assume that there are at least, we take 10 times 500, we assume will be at least is 5,000 for the populations. And then that satisfy all the conditions. And remember, for this type, if usually second and third condition is not met, then you don't have to do further action. Okay, I try to erase that, but I assume I cannot. Okay, so if I'm done, then you apply the formula, and you found S equal to the square root of P times 1 minus P. And again, remember, P or P hat is okay. Okay, it's just the same thing. Okay, divided by n equal to a square root of that. Plug in the value, we got 0.022. Okay, 0.022 is mean like about 2.2% of the error. Right, and very small. So here to find the probability that proportions in the sample is greater than 63%, we can use technology to find the probability of getting the larger than 0.63 in a normal distribution. You put that in. So this maybe you using for TI-84. But later I will use, I help you, I'll show you to use StatQuant for this one. So here using StatQuant, I think this is using StatQuant. Yes, so this is the picture that's describing, we are looking for the probability right here. See on the right side, because they're talking about more than, which mean the right side. More than 63% is mean the right side. Because 50% is in the middle, right? 50% will be on the left and the right side. 50-50, you count from the left to the right side, probability will be increasing. So that's why 63% will be around right here. The probability that the proportion of female in the sample will be more than 63% is about 0.0345. So that would be, this part is 0.0345, which means equal to 3.45% that female, probably the proportion of female in the sample, female what? Go back to the story. The story is still talking about the proportion of female in our sample will be more than 63%. Okay, that's what it is. Sorry. Okay. I try to erase this. Eraser tool. So, okay, later I will make a video about StatQuant, talking about this chapter 7 and chapter 8, for you to look at, to see how I run it. And don't forget to watch more video from Pearson. They have more example for you to look at. Next example, example 2. Okay, in a closely contested school bonds election, polling indicates that 50% of voters are in favor of the bond and 50% are against the bond. So like P and Q are is kind of the same, right? Or you might say it's P hat is the same with Q hat. Suppose a random sample of 80 voters is selected. They're asking us all three, instead of they just keep asking right away what is the probability, blah blah, but they give you steps. Because if even they don't write down the step for you like this, you have to automatically testing by using the central limit theorem. If that if central limit theorem apply before you do work. So this is look like the answer is percentage would be expect favor the bond will be 50. You see that? We have 50 expect favor and the other 50 is not. So we got 50% is will be the answer for number 1. Does the central limit theorem apply? This apply when you're testing all 3 conditions for me. Number 3, what is the standard error for this sample proportion? It means after number 2 satisfied, you can go ahead and find SE by using the formula of SE for the sample distribution. And then you're testing is it if that the standard error is falling into 2 standard error. Falling into within 2 standard error is mean they're talking about 95% in the middle of, of the data. Right here is the solutions for number 1. The answer is like about 50% favor of the bond. Number 2, of course, it's random sample is random and independent, and the testing for second condition is NP. Multiply that, you got this value greater than 10, and so on. As number is large enough, the condition 3 is they take the number of n times 10 give us 8,000. So that's all satisfied. 8,000 is greater than 10. So in this 3, find the standard error by using that formula. We are having 0.0559. And number 4, in order to compare, if 0.0559 0.0559, which means 5.59%, right? So we're talking about if is it within, so this is standard error, is it within the two standard error? So we're gonna say it's a bit out, right? Because 95% we are having 95% in the middle like this, right? Two standard error, this is our mean. One standard error right there, -1, is 2, this -2. So this is, we call 75% of the data right here. Okay, so, and we are having the standard error is 0.0559. It means we multiply it by 100%, we have 5.59%. So compared to 95% with this, we have, if we have like about 50, then it's good. But look like right here, so by empirical rule, this is by empirical rule or by if you remember, 68%, 95%, and 99.7%. This is, we call empirical rules, right? We know that the probability that the sample proportion will fall within two standard error of 0.50 is 95%. We could also verify this using the technology. I would like you to see the picture, the actual picture like this. Okay, so that's represent for 95%, and you can either this is confident interval. Actually, they didn't say clearly, but this is a confident interval. Let me erase this and give it to you. So the confident interval, they are having p minus 2se, comma p plus 2se. For in this case, the confident interval that they're asking if it's fall within two standard error, and we found the value is 0.3882, comma 0.6118 will be the confident interval. From here is 0.388, and here is 0.6118. So this value here, the data is 95% is within this interval. So that's why we're having the answers. The probability of being within two standard error of the mean is 0.9545%. We can estimate as 95%. The key idea, if the condition of the central limit theorem are met, the probability of a sample proportion will fall within two standard error of the population value is 95%. So that is the general idea. All the time, they're just like giving us that question to proving that all the time that the central limit theorem, if the central limit theorem are met, all the time the data will fall within two standard error. According to American Veterinary Medical Association, we have 36.5% of the Americans own a dog. Suppose a random sample. All the time you see the word random right there. We're talking about this type of question. You find SE, you figure out probability, like that. And then for this one, we're doing the same things. We're having the same step. We check for the central limit theorem, and we find the standard error like this. Okay, so after we got the value right there, in order to answer this question again, you can use empirical rules to apply to find the if it's 45%, is it and to answer the question like I asked like this, would it be surprising to find that 45% of the sample own a dog? So then we can using they're using kind of we call 95% empirical rules right there. But this time they only find the right side because 45% look like they said more than 2 standard error or not. Then you can testing just plus 2 SE to figure it out. And that's 45% is look like it's bigger than the actual value that you found from the mean. So that would be surprising. For this type of problem, 7.3, they're just focusing on we call sample distribution. And all the time, like I said, you see the word random sample, then you apply this type of question. Especially you have to test for central limit theorem before you find the standard error all the time. And from there, you will find probability easier by using StatQuant. Again, this is online class, so I don't teach you how to use TI-84, TI-89. But for StatQuant, I will record different video for you to watch. How do I run StatQuant? And also, Pearson do have many video about that too, so please take a look at that too. Okay, thank you very much. This is 7.3. I'm finished. We have, I think, let me go back to see how many section. 7.4 and 7.5, and we finished chapter 7. Okay. Okay, so I end recording right now, and I will open a new recording next time.